All right. Hello. Sorry. Okay. So good afternoon again, everybody. I was starting.
Okay, sir.
Hello. Can you hear me now?
Yeah, I can hear you, sir. Good afternoon.
Okay. Yeah. Thank
Yes,
you.
yes, sir. Can hear you. Good afternoon.
Yeah. I was talking for a minute and then I realized I'm on mute. Probably still part of the jet lag. But yeah. Good afternoon, everybody. I hope you had a good time with the reading assignments and the video recordings for last week. I just got back from my travel, my official travel to the UK, 4 a.m. this morning. So that's why my voice is still feeling some of the fatigue due to the length of the travel that we had to go through the past 2 days actually, and we were stuck in the airport last night for 3 hours just trying to pass through immigration. But yeah, but for today, I'll finish our discussion on graph theory or graph theory, some ideas from graph theory that will pop up in most data science applications. um, I want to focus on this because these are the terminologies that you will encounter when you're dealing with neural networks or network analysis. And they are the things that are happening behind the scenes. And also, they're very helpful whenever we are doing some machine learning, when we are running machine learning algorithms, like in clustering and classification algorithms. So these terminologies will be very helpful for you, and this will also help you in the future if you will need to modify some existing machine learning algorithms for your particular application or your particular type of data. All right. So that's our program for today. But looking forward, I was chatting with Dean Jomar before I started the meeting, and we agreed that I will be handling the sessions until May 18. So you'll have me until next week. On Thursday, I'll start talking about actual machine learning algorithms, either classification or clustering, and then we'll continue with the rest on next week. So I hope by Thursday you have your MATLAB ready with you. If you're downloading MATLAB, make sure that you downloaded the machine learning toolbox. All right. But you don't need to use MATLAB. If you're more familiar or comfortable with Python or R, you can use them, but I know just a little bit of R. I refuse to learn Python for whatever reason. Partic- uh, yeah, one reason could be that I am not really um, I'm not comfortable with the syntax or the type of syntax Python use, but that's just a personal preference. But yeah, but the demo I'll present to you on Thursday will be using MATLAB, and I'll show you how user friendly it is insofar as their machine learning app or their classification app learner is concerned. So it's very user friendly. So that's what I'll try to share with you next week, and then I'll give you the final problem set for this course, which for my end of this course, which will probably take up a bigger portion of your final grade from me. So we'll talk about that on the 18th. And then the last few weeks towards the end of the classes, that will be free for you to finish all the problem sets. So I'll just need to clarify with Sir Jommer, but the way our conversation through chat went earlier is that the lectures will be until the 18th, and the rest of the times will be for you to finish all the problem sets. So I think you need to devote at least 1 week for the problem set under my name that I'll give on the 18th. Okay? So I hope that's okay. That's fine. Fortunately, I'm using only one device, so I can't see your reactions, but I hope it is okay.
It's,
All right.
it's okay, sir.
Okay, thank you. So now let's move with the slides now. So I think we finished at this juncture last time, right? The rest were 10 minutes, so we made it a 1 week break. But anyway, so let's go talk about paths and distances. So still, these are some graph theory terminologies that could be helpful later. So first we talk about paths. So here a path is a route that runs along the edges of the graph. So we assume that each edge a path visits is distinct. So this is one path, a path of length 1, because there's only one edge that is traversed by the path. Now this is path 2 with length 3, right? This is a path of length 3 because there are 3 edges. So we say this is a path from vertex 1 to 4 going through 2 and 5. So really it's just traversing edges from one vertex to another. Okay, so that's what we call a path. Now this is more of a intuitive notion of a path. If you are into graph theory, there's a more what you call this? There's a more definitive definition for a path. But basically, it's just going through edges, right? So look at this. I'm starting from 1. I traverse this edge going to 2, and then from 2, I went through this edge to get to 5, and from 5, I traverse this edge in order to get to 4, right? So do you see the laser pointer? I'm not sure if you can see it. No, you can't see the laser pointer. Or maybe I'll use the annotation.
Yes, I'm seeing it, sir.
Okay, thank you. So yeah, that's what we call a path, right? And then a path length represents the number of edges. Probably this is the one that this is the one I told you about earlier. Path 2 here that we consider, the path running from 1 to 5, then 4, is a path of length 3 because there are 3 edges. This is edge number 1, edge number 2, edge number 3. So this is a path of length 3. Now, the shortest path or geodesic path between nodes I and j is the path with the fewest number of edges. The shortest path length is called the distance between nodes I and j, denoted by d sub ij, right? Now, if we consider the vertices 1 and 4, and we want to compute the distance between these 2 edges, we need to consider all possible paths that will lead us from vertex 1 until vertex 4. For instance, we have path number 1. Path number 1 is of length 1, and that will give us directly from 1 to 4. And that's the smallest possible path going from 1 to 4. Of course, remember, we also had path number 2, right? That will also bring us from vertex number 1 to vertex number 4, but it will take 3 edges to get from 1 to 4. So even though it's a path, we don't consider it to be the geodesic path. The geodesic path is the path of shortest length. And the distance between 1 and 4 will be 1, right? We denote it by d sub 1 form. The distance from vertex 1 to vertex 4 is the length of the shortest path from vertex 1 to vertex 4. Okay? Now, we can have multiple shortest paths of the same length between a pair of nodes, and the shortest path never contains loops or intersects itself. So some notes over here. So for instance here, let's look at the path, or let's look at the distance between vertex 2 and vertex 5. So between vertex 2 and vertex 5, there are several paths that we can consider, right? We can consider the path 2, 3, 5, right? The path from 2 going through 3, then ending up with 5, that is of length 1. That's of length 2, right? Then you can also have the path starting from 2, traversing 1, getting through 5, that's also of length 2. Actually, there's some other few. We can have 2, 1, 4, 5. Right? So we start from 2, go to 1, then go to 4, then go to 5. That's the brown edges, right? But what is the length of that path? That's 1, 2, 3. That's of length 3. Okay. Then we have what? We also have I think that's all the paths from 2 to 5, right? Now, you see that the shortest paths are 235 and 215 because both of them has length 2. So we say the distance sub 2 comma 5 is equal to 2. Jan has a question. The length of each path are assumed to be the same. It depends on really counting the number of edges that will bring you from the number of edges that you traverse in the path. So here we have 235 and 215 both having 2 edges, but 2145, that path, right? That's another path leading us from 2 to 5, but that will require us to traverse 3 edges. So this is the first edge, this is the second edge, and this is the third edge in the path 2145. So here we have presented 3 different paths, and they have two possible values, either 2 or 3. So here the shortest path is of length 2, right? So that is the distance between 2 and 5. Although we have found another path that is of length 3, but since it has a larger path length, then we will consider 2 to be the shortest path, which is the distance from 2 to 5. Okay, so different paths will have different lengths. It really depends on counting the number of edges that you need to traverse in the path, right? But the shortest path the shortest paths will have the same values, or that will have the same length. So 235 and 215 are both shortest paths, and they do have the same length. Okay, so I hope that answers your question, Jan. Okay. Now, another way to characterize graphs would be to do a distance matrix. The distance matrix is really a matrix that takes into that stores the distances between 2 vertices. And here's an example for the graph on the left. You see that the diagonal entries are all zeros because this diagonal entries represents the distance from vertex 1 to vertex 1. That's this value. This guy, the second diagonal entry, is the distance from V2 to V2. And of course, you don't need to traverse a path in order to get to the same vertex, right? So that's a path from a vertex to itself that would be of length 0 because you don't need to traverse an edge in order to get from a vertex to itself. All right. Now let's look at why do we have an entry 3 here. Let me just clear the board. Okay. So why do we have an entry 3 over here? If you'll interpret that entry, that is the distance from vertex 3 until vertex 2. Vertex 3 is right over here. Vertex 2 is over here. And luckily, there's only one possible path from vertex 3 to 2, right? And that is this path. So we go over here, this edge, from 3 to 6, and then from 6 to 7, and then from 7 to 2. And that length is 1, 2, 3 of length 3. So that is guaranteed to be the shortest path from vertex 3 to 2, right? Now, I think the furthest vertices from each other are vertices 3 and 4, because the shortest path between V3 and V4 is of length 5, right? So V3 is here, V5 is over here. So we need to traverse this, this, and this. 1, 2, 3. Sorry, V4. I thought it's V5. Hold on. So I am checking this guy. Oops, sorry. So we're checking which one again? This guy. So that's from V3 to V4. Sorry, I thought it's V5. So the distance matrix tells us that there's a path of length 5 from vertex 3 to vertex 4, and that's the shortest path, right? So let's see. So from 3, I'll go here. That's 1. Then on 6 to 7, that's 2. 7 to 2, so that's 3. Then here 4, and then 5, right? So that's one of the shortest paths from 3 to 5. Actually, there's another. So the one I traced here is 3, 6, 7, 2, 1, 4, and that's of length 5 because there are 5 edges needed to be traversed over that path. But the path 3, 6, 3, 6, 7, 2, 5, 4 is also a path from 3 to 4, and it also have length 5. All right. Is it clear? Is the distance matrix clear? Okay, I hope it is. Though I'm not seeing any reactions. Probably I'll try joining through my phone because I can't see your reactions. Hold on, guys. Okay, there you go. I hope I will see your reactions on my phone. So I'm not used to doing a lecture with only one screen. But anyway, so let's see. All right, so and it is everything clear about paths and distances plus the distance matrix? But I guess one possible problem that you will be thinking of would be how to construct the distance matrix, right? If you have a small network such as this graph that we have on screen, it's easy to find the distance between a vertex and another vertex because we can just what do you call this? We can just exhaust the paths leading us from one vertex to another. But if you have a very complicated graph, a very huge network, that could be a problem. Finding the shortest path between one vertex to another. And probably later, I'll show you one algorithm that will tell us how to compute the distance, or equivalently, how to find the shortest path between a vertex and another. Okay. So if you have that question on your mind, just hold on that thought, and we'll discuss how to find the shortest distance between two vertices. All right, or not the shortest distance, but the shortest path between two vertices. Okay. Now, on another graph graph parameter is the diameter of the graph, and this is the longest distance in a graph. So you'll just look at the distance matrix and look at what's the maximum value inside the matrix, because that will represent what's the longest shortest path from one vertex to another, right? So this is a measure of how far are the furthest vertices from one another, right? So in this particular case, if you look at the distance matrix, the maximum value in the matrix is 5. So we can say that the diameter of this graph is equal to 5, right? Because the furthest graphs, the furthest vertices from one another are vertices are 3 and 4, which has distance 5, right? So that's the diameter of the graph. So if the diameter is very large, that means there could be isolated cases wherein it's hard to reach one vertex from another vertex. But if the diameter of the graph is very small, that tells us that all the vertices are tightly packed in the sense of paths. All right. Now, okay. Now, if I add an isolated point here, for instance here, I consider the same graph we had before, but I added an isolated vertex. All right. An isolated vertex is not connected to any other graph or in any other vertex in the graph. So look at vertex 8. It doesn't have any edge connecting it to any of the other vertices. And if there's an isolated vertex, we can say that the diameter of the graph is infinity. All right, because the distance of vertex 8 from any other vertices in the graph is equal to infinity, because there's no way we can create a path from any vertex to vertex 8. All right. That's why you can say that the graph diameter, if the diameter of the graph is very large, it gives us little to none information about the density or about the closeness of the vertices in the graph, because one isolated point can ruin the interpretation of the graph diameter. Because prior, say, to the introduction of vertex number 8 here, our graph has diameter 5, right? But when I added that 8 vertex, the diameter became infinity. And that's only one isolated case, right? So that's why I think the graph diameter is useful whenever the graph diameter is small. But if it's too large, we could be dealing with just some outliers, right? Just like the isolated vertex I have on screen right now. Okay, now that's why a more interesting or more useful graph parameter is the average distance of the graph. So what we'll need to do here is to take the average of the entries in the distance matrix, excluding the diagonal, right? And then we denote the average graph distance by bracket D. Okay, so you'll just erase the entries in the diagonal because they are all zeros anyway. And then we take the average of all of the entries. Again, we'll have a problem if there's an isolated vertex wherein the value would be infinity, right? So then the graph distance will also be infinity. So one possibility is for you to take away all the outliers. So you can do a box and whiskers plot, and then take away all the outliers and then compute the modified graph distance. I think that will be better for some other applications. Okay, now just a quick remark here. The concepts of path length, shortest path, diameter, and average distance can be redefined for digraphs and weighted graphs. For instance, here, each edge could be marked with a weight, and then we need to factor in that weight in computing the distance between or the distance between two vertices. For instance, let's look at the distance between vertex A and vertex C. Right? Now, let's do vertex C to A instead. So let's do, okay, hold on, let me erase that. So let's do distance from vertex C to A, right? Now, we have a weighted graph, and it's also a digraph or a directed graph. So arrows tells us where we can go from a certain vertex to another, and the weights tells us what's the cost of traversing that edge. Now, if this was an unweighted graph, then we can say that the distance CA is equal to 1 because there's an edge allowing us to get from vertex C to vertex A, and that is this single edge, right? However, if we will consider the weights, or we'll consider this as a weighted graph, the cost of traversing that one edge, this edge over here, from vertex C to A is 8 units. But if we will traverse the path CDA, so from vertex C, I'll go along this path, this edge to get to vertex D, and from vertex D to get to vertex A, I'll traverse this path. So that will only cost me 4 units, right? And are there any other possible paths from C to A? So there's only 2 ways to get out of C, and that's going straight to A or going to D, so that's fine. And there's only 1 way to get out of D, and that's via this edge going to A. So I think that's there are only 2 paths leading from vertex C to A, and the shortest between these 2 paths has weighted length 4, right? So we can say that the distance between vertex C and vertex A is equal to 4, right? So that's how we redefine, or how we modify the definition of the distance for weighted digraphs, okay? So everything's good? All right.
I want to ask a question.
Oh, go ahead.
I want to know whether the distance matrix is constant for any problem.
Oh, why the distance matrix is not a constant?
Where is it fixed? You have fixed, you use it to solve problem.
Well, for a certain graph, it will be fixed. So for instance, if you're considering this graph, there's a unique distance matrix corresponding to this graph. But if you have a different graph, that's when the entries of the distance matrix will be different. Does that answer your question, or are you referring to something else?
No, it's okay.
Okay, right. So that's very difficult, because if I give you a different graph, you will create a different distance matrix. So if you have a very complicated network, a very huge graph, then computing the distance matrix will be a huge pain, because there are lots of edges, a lot of paths to consider. Okay. All right. So another graph parameter is the closeness of a vertex to all other vertices in the graph. So in a connected graph, meaning when we say connected graph, there is a path from any vertex to another. So we are removing the possibility of having isolated vertices, right? So in a connected graph, we can reach one vertex from any other vertex through a path. So we don't have the problem of isolated vertices. And the closeness of that vertex is the reciprocal of the sum of the distances of U from all other vertices. Okay. So in essence, this is really the reciprocal of the average distance, sort of vertex U from all other vertices. Now, I say sort of the reciprocal of the average because some books multiplies this value by n-1 to make it the reciprocal of the actual average of the distances from vertex U to all other vertices, right? But since n-1 is just a scaling constant, we can forget about this because that will not change. That factor n-1 will not change if we're dealing with one vertex U and any other vertex V. So we can just drop it. Again, it's just a scaling constant. So we'll just take the reciprocal of the sum of the distances from vertex U to another vertex. So that's the closeness of a vertex V. So it represents how close the vertex V is from all other graphs within the network, all other vertices from the network. So just a quick example, in an undirected graph, let's reconsider this distance matrix over here. The closeness of vertex 1, since this is undirected, I can go column wise or row wise. In this particular case, I'll just go row wise, but you can do column wise because the matrix anyway is symmetric, right? So from vertex, the closeness of vertex 1 will be the reciprocal of the sum of the row entries, all right? So this is 5, 6, 8, 11, 13. So the closeness of vertex 1 is 1 over 13, the reciprocal of the sum of the distances of vertex 1 from all other vertices, right? And then you can compute the same for the other remaining vertices, okay? Now, if it's a directed graph, you need to be careful, right? So you can, if you're starting with the column header telling you where is the starting vertex, and the row header is the terminal vertex, then you need to go column wise, all right? Starting vertex to the ending vertex, so you go column wise. So probably as a it would be easier as a matter of convention to accustom ourselves to computing the closeness to be the reciprocal of the column sum instead of the row sum. Just to employ a common standard for directed and undirected graphs, right? So following our conventions, let's just compute the closeness to be the reciprocal of the column sum, all right? Because it will matter which you sum up whenever you're dealing with directed graphs. But based on our conventions, it would be better if we will just take the column sums, all right? Okay. Now, I want now to give you an example of a network analysis tool, though I won't have time to show you a MATLAB code for this. Probably next meeting I'll show you, but I'll give you illustrations of an ego network, which is essentially a nice example of data analysis using graph theory, right? So an ego network is defined as a portion of a social network form of a given individual. We call that individual the ego, or the center of the network, and the other persons with whom they have a social relationship called the alters. So here you start with an ego, and then you determine a relationship that will connect that ego to other persons within the network. And those persons, other persons, are called the alters. For example, I generated this graph using Mathematica. I think this is in way back 2014, when Facebook is still very lenient sharing data or allowing users to download their data. So essentially, I can say that this is my ego network, which is my ego network in Facebook. So every node or every vertex in this network are my friends in Facebook. All right, and the nice thing is that the way Mathematica presented the graph of my ego network is quite telling of what, or in what social instance or in what social context am I in which social context I met these persons in the network, right? Because it clustered together all of my friends that are also friends with each other. So I think there are possibly two main components. So you have this group over here, or this cluster here, and this cluster over here, right? These are two major clusters. The size of the vertices tells me how much interaction I had with these persons, and two vertices are connected by an edge if they're also friends in Facebook, right? So when I was looking at this data, because I did my undergraduate and MS my MS thesis on graph theory, so this is one of my illustrations in my thesis, right? So based on looking at the data, I can see that this group, this cluster, refers to my family and personal friends from my locality, and this bigger chunk are my social my Facebook friends that are basically based in UPLB. So the way the graph was drawn gave me right away a context on which I met these persons, right? And then I see that there are also some members of my family and friend circle in my province that are also friends with some persons I know from UPLB. And then there are three isolated vertices here. I was thinking where they can come from, and I realized there are friends. They are either my pseudo accounts that I friended with myself just to give me gifts in Facebook games. Remember when Facebook started? It's very famous for its games. It's social games that you have to gift one another, and I was quite addicted to them. That's why I needed to create some accounts in order to gift myself. Then I also friended some random persons just to give me gifts through in this Facebook games. Right. So that's an example of an ego network. And then for each of all of these vertices, you can compute the distance, you can compute the closeness, you can also compute the diameter of this graph. Although the diameter of the graph here will be infinity because there are three isolated vertices, but I don't remember what is the modified diameter. That is the diameter if I just ignore those three isolated vertices. Okay. So, but this is a good example of an ego network. Unfortunately, now Facebook shut down the access to or the at least Mathematicus access to Facebook data. I think they also shut down MATLAB access, or they have shut down access to any other computing software. So it's very tricky to create your own ego network. I was thinking that to be your final problem set, or not final, one of the problem sets, but I tried it last semester and I wasn't able to generate the data again because again, Facebook has stricter data privacy rules right now. So it's really hard to get data from them through a third party software. I think you can download it for yourself, but making the graph uh is yeah, doing the graph from scratch manually is very difficult, especially if you have hundreds of friends in Facebook. Yeah, Jihan, I didn't use Gephi here. I'm not familiar with that software. I just used Mathematica here, right? But if you know a software that can generate this type of graphs, then that will be great. Okay. Oops, let me. Okay, so here's an example of another ego network. This ego network is from the Stanford Large Network Dataset Collection. I just don't remember. This is from a random person. So it's the Facebook dataset of a random person. Of course, that person was not named in the Stanford uh, large data set collection, but it has a total of it has order 3,959. It has size 84,243. And there are one, two, three, I think four egos in here. Okay. So maybe I can show you next time or on Thursday how to generate such a network from using MATLAB by just invoking the Stanford Large Network Dataset Collection. Okay. Another one is this, and this is the ego network of Facebook page likes, right? So here, each vertex stands for a company or an organization. I think in this particular case, we have 5 egos: Make a Magazine, NOAA, NWS, Maker Fair Rome, and Maker Fair. And 2 edges are connected with each other if they're connected through likes, right? Probably if a person liked if a person liked both organizations, then those 2 organizations will be connected a via an edge. Right? And I think here the in degree, this is a directed graph because oh yeah, sorry. This is if a page liked another page. It's not a third person liking both pages. So 2 vertices will be connected by an edge if the first page like the other page, right? So for instance, I think the arrow is like here in this particular example. So that means this organization, this Facebook page, like this other page. And it may not be mutual, so it's that there's only one edge going through one direction between these 2 vertices, right? And then you compute the in degrees. I think the highest in degree here is around 107. I just forgot the exact number, but if we'll have time on Thursday, we can regenerate this graph and then compute the other parameters that we considered before. Yeah. Now, this is probably one algorithm that is very famous, right? And this is very helpful in computing the shortest path in a graph. This is one of the problems that I raised earlier insofar as creating a distance matrix is concerned. Because again, if you have a very complicated network, computing or finding the shortest path will be difficult. So Dijkstra's algorithm is one of the most famous algorithms in graph theory, and this will tell us what's the shortest path. Now, it is sort of an exhaustive way of or a brute force way of finding the shortest path, but we are doing it in a systematic and organized manner. So we're sure that right after the algorithm is done, we'll get the shortest path. Or actually not the shortest path immediately, but we will find the distance between one vertex and another. Okay. So the actual algorithm is summarized in this page. I lifted it in Wikipedia, so that algorithm in Wikipedia is correct. So you can comfortably just copy what is in that page in this page. I review it and it's correct, right? Now I'll not go through all of the steps by reading this slide. I'll just show you how it is done, and I think that's better. But if you will be writing a code for the algorithm, if you want to practice your coding skills, you can just visit this page for the step-by-step account of the algorithm. But I'm sure you can download a code for Dijkstra's algorithm in any programming language, because this is one of the most useful and famous algorithms in graph theory. Okay, so let's consider this network. All right, so it has 9 edges, and say I would like to look at the shortest path starting from vertex 1. So sorry, not vertex 1, but from this vertex, right? So I don't know if I can keep the annotations, but hold on. I want to label all of the vertices with a name so that we can refer to them easily, because the labels here will change later. All right. So I'll call this vertex 1. I'll call this vertex 2. So never mind the labels on the labels on the on the vertices themselves, because we will replace them by the shortest path, or the length of the shortest path from vertex 1 to that particular vertex. So these numbers 1 to 9 on the vertices will be replaced by the distance from vertex 1. So that's why I'll need to relabel all of these things. So I'll call this vertex V3. Let's call this vertex V4. Then I'll have V5 over here. And then V6 here. Then this is V7. And this is V8. Then finally, this is V9. Okay. In this run of the algorithm, I want to find what is the distance of vertex 1 from all other vertices, vertex V1 from all other vertices, so that we can create the column for on the distance matrix corresponding to V1. All right. And we'll do so using Dijkstra's algorithm. Okay. So here's the first step. Let me just stop my annotations. Okay. The first step in the algorithm is assigning a 0 value to the starting vertex. Again, I want to start at vertex V1. So this is vertex V1. I want to start at that vertex. So I will mark it with a 0, because the distance from V1 to itself is 0, right? You don't need to go through any vertex to end up with V1, right? But there's another path going from vertex 1 to vertex 1. So we can go V1 to V2 to V3 and to V1. But what is the cost of going from V1 to itself via the path V1, V2, V3? That's 4 plus 1 plus 3, that's 7 units. So it's easier to stay at V1 rather than take that path, because it will be more efficient, right? So we will assign 0 to the initial vertex. And then we will assign infinity to all of the other vertices in the network, all right? Because the number in these vertices will represent the shortest path. So we will be updating the numbers inside the circles to represent what we have found so far to be the shortest path from vertex 1 to them. Okay? Now, I'll update the neighboring vertices of the lowest valued vertex. So the lowest valued vertex is 0, all right? Because look at this. There's only one labeled with a finite number, that's 0, so that's the least. So I will update the value of all the neighbors of B1 with the cost of going through a path from V1 to that vertex. Luckily, V1 also only has one neighbor, right? It only has V2 as a neighbor, because there's only one outgoing edge from V1, and that's going to V2. And the cost of going to V2 via this edge is equal to 4. So that's why the label here became 4 from infinity, because so far we have found a shortest path from V1 until V2 that is shorter than one that has length infinity. So that's gonna have the label 4. Okay. And then from 4, okay, from V2, because that's the lowest valued vertex now. We're done with the one labeled 0, so our focus now will be on 4, and we will compute what are the we will update the numbers inside the neighbors of V2. V2 has two neighbors, V3, because we can go through this edge, from V2 until V3, and then V4 is another neighbor, because we can go through here. And then the thing here is we're computing for the shortest distance starting from V1. So the labels on each of the vertices will be the cumulative distance from V1, right? So that means you're always your point of reference is always V1. Okay. So here from V4 from V2 going through V3, it will cost only one step. But in order to reach V2 from V1, we already spent 4 units. So the label here for V3 will be 5. Okay. Because again, that's the cumulative distance from V1 until V3, right? So you got the 4 here, and then from V2, you need to spend 1 unit to get to V3. And then 5 is smaller than infinity, so we replace infinity by 5, right? That means the shortest path we have seen so far from V1 to V3 is of length 5. Okay. Is everything clear so far? Let me know if you have questions. Okay, everything's good, I suppose.
No, sir, everything is not too good.
All right, great. So and then what would be the label for V4? What do you think will be the label here for V4? What will I replace infinity with?
Come back, I get you.
Yeah, so what will be the value here? Okay, Jan is right. Did you guys also see that that should be replaced by a 9, right? Because from V2, it already has a value of 4, and then you add the 5, so you'll get a 9 over here. So in the next step, we have updated the values for V3 and V4 to 5 and 9 respectively, okay? There we go. And then let's now consider V3, okay? Because that has the lowest value so far. So we can select from 5 and 9, but the smaller is 5. So let's consider 5 for now and see where we can go, right? Now, from here, V3 has 2 neighbors. Actually, I'm going off script here, but I should have started with V4 first. But anyway, so here V3, okay, there are 2 neighbors, right? V1 and V9, because there are 2 outgoing edges from vertex V3, right? 5, we already have a value 5 here. To get back to V1, that will cost us 7 units, right? 5 plus 2, that's going to be 7. But 7 is larger than 0, so I won't change the 0, okay? Because again, we're looking for the shortest path. So the smallest numbers will always prevail, right? So I will not change the 0 here to 7, okay? Now here, V9, you will see later that it will be replaced by what? It will be replaced by 11. Okay, because you have already 5 units spent to reach V3. I'll need to take an extra 6 in order to bring us to V9. So a total of 11 there. But I guess in my script, yeah, there you go. Okay, and then let's try to move forward. Let's go with V4, right? So V4 only has 1 neighbor. Its only neighbor is V5 because there's only 1 outgoing edge from V4 until from V4. And that outgoing edge has cost 1. So this guy will be replaced by 10 units, right? Okay. And then it still has the smallest value. Oh, by the way, I'm also labeling all the edges or marking all the edges that we have traversed because I want to keep track if we have gone through all the possible edges. So here we have, I'm coloring them purple just to tell us that we have already gone through that edge, all right? And then once all the edges are colored, then we are done, all right? We have completed Jigsaw's algorithm and we can find the distance between vertex 1 and all the other vertices, okay? So now what's the lowest value so far? 10, right? So we have the 10 here. We're already done with the 9, so it's already finished. So we'll go with 10 V5, and then V5 has three neighbors. The V6 going through this edge, V7 going through this edge, V9 going through this edge, right? So V6 will have label 11 now. That's 10, the original value of V5 plus the cost of the edge, that's 1. This will have 12, and this will have 19. Okay? So those are the numbers, and all the edges are colored. And then we'll now go to 11, the 11s, right? So the 11s here, because we're already done with the 10s, right? Now, vertex V9, all right? V9 has how many? Has two neighbors, V2 and V3. Now, from V9 going through V4, okay? So it's gonna be 11 plus 4, that's a 15. And that 15 units is greater than 4. So we will not change the value 4 over here, right? Because that means we have a shorter path from V1 to V2, rather than going from V1 to V2 and then going to V9, going to V3, and then going to V9, which will cost us 15 units. We can go directly from V1 to V2, right? So that will be unchanged. And then here from V9, it has another neighbor is V6, but it will take 14 units in all. But we already have a value 11 there. So